We're given that phi is equal to a half times root 5 plus 1. In fact, this is the golden ratio. And if you've not heard of that before, I'd advise you look it up. Very interesting mathematical number. In this question, we're asked to show, first of all, that phi squared is equal to 5 plus 1. So I'm going to do that by starting out with phi squared. And that's going to be, we can square both the half to give me a quarter and the root 5 plus 1, which I can write as root 5 plus 1 times root 5 plus 1. So then I'm going to get 5 plus root 5 plus root 5, so it's going to be 2 root 5 plus 1, which is a quarter, times 2 root 5 plus 6. And now I can either imagine, there's two ways I can think about it. I can either factorize a 2 out of here, and when I factorize a 2 out, it's going to become a quarter times 2, which is a half. Or I could actually multiply through by a half, okay, and leaving a half on the outside. In both cases, I'm going to be left with a half, and then root 5 plus 3. Okay, I'm nearly there. I've nearly got it, but I've got a 3 here at the moment. So I can write this as plus 1 and plus 2. And I can just multiply out some of the bracket. It's going to be a half times this plus a half times this. That's going to give me my plus 1. I feel like that's enough working. And there I have it. I've got 5 squared is equal to 5 plus 1. Okay, nice. So that was part 1. Now I'm going to try and show that 1 over phi is phi minus 1. And that is going to be 1 over a half root 5 plus 1. And because I'm dividing by a half, I can immediately make that so I'm timesing by 2. Just get it as a more, so there's no fractions within fractions. Okay, then I just need to rationalize the denominator because I want to get it as phi minus 1, remember? So I'm going to times by root 5 minus 1 over root 5 minus 1. That's not going to change the fraction, just using the idea of equivalent fractions. So that'll give me 2 root 5 minus 1. And I'm going to times these brackets together, so I'm going to get 5. Then it's going to give me minus root 5 plus root 5 minus 1. They're going to cancel. And I'm going to get a half because I'm going to get 2 divided by 4, which is just a half, times root 5 minus 1. And this is going to equal a half root 5 minus 1. And then I'm going to write plus 1 minus 1. So I've not changed it. I've just done this because now I can bring the 1 inside the bracket. Root 5 minus 1 plus 2. Basically factorized a half out of the 1. So I've got a 2 inside. The reason being that now I can write it in terms of phi. It's going to be a half root 5 plus 1 minus 1, which is phi minus 1, which is what we needed to show. Okay, good so far. Okay, let's take a look at the next part. So we've got the equation of two curves given by y equals 1 over x and y equals ln x minus x plus k. K is a positive constant, and of course we've got some domains here. Curves touch at point P, and find in terms of phi the coordinates of P. Right, so if the curves touch at P, let's just have a think about what these curves might look like. 1 over x is not too difficult to draw. This one's going to be harder though. The ln x is actually, let me just draw it temporarily. It's going to, ln x looks a bit like this, but then minus x is like this. So if you add them together, you're going to get something that starts out being negative down here, and then it's going to kind of come up, but then it's going to come back down. For it to touch, it must be that it just like glances off and then comes back down. And it's going to be the K that kind of works this out. So it doesn't just like go above it and come back down, then it wouldn't be touching, and it doesn't sort of miss it. Okay, so it's going to look something like that. It's just going to be one solution as well. So importantly, what is happening here? Well, the two functions are going to equal, and so we can set them equal to one another. But also something else is happening. Because they're just touching, that means they're temporarily going to have the same instantaneous gradient. And that's going to be a thing to use because when we differentiate this one, the k is going to disappear. So when they touch, they will have the same gradient. I'm not actually interested in that gradient. We just care that they're the same thing so we can work out x. So for this one, I'm going to get, I can write it as x to the minus 1. So I'm going to bring the power down to be minus x to the minus 2. When we differentiate ln x, we're going to get 1 over x, then it's going to be minus 1. Therefore, at p, minus 1 over x squared is going to equal 1 over x minus 1. I can times through by x. I mean, like, something in the back of our minds has to be these relationships from the start. Okay, because we're asked to leave our answer in terms of phi, so it's got to be that we use these relationships somehow. So at the moment, yeah, I've got a 1 over phi, but I've got a 1 over minus 1 over x squared. Um, hmm. I think it's best to multiply through by x squared. So I'm going to get minus 1 is equal to x minus x squared. And this is looking good because then I'm going to get x squared is equal to x plus 1. And therefore, using a, x is going to equal phi. This is a quadratic. There's actually going to be two solutions. But if you were to write it out as x squared minus x minus 1 equals 0, you could quickly see that when you put it in double brackets, one of these solutions is going to be positive and one of these is going to be negative. And there is not going to be a negative solution. So I can ignore any negative solution. I think it's important to say that. And when x is equal to phi, y, I can substitute it back into either one. It's going to make sense to put it back into this one rather than with the k. It's just going to be 1 over phi. So p is going to be phi 1 over phi. Of course, we've got that 1 over phi is phi minus 1. So we could write it, arguably it's slightly nicer because there's no reciprocal going on like that, but either one of these is accepted. The last bit then is to work out the value of k. And for that, we can substitute p, the coordinates for p, into here. So at P, we're going to have 1 over phi is equal to ln phi minus phi plus k. It's going to make sense now to change that 1 over phi to phi minus 1. And from that, we can get k. K is going to be 2 phi minus 1 minus ln phi. I guess I could have left it in terms of 1 over phi, but this just seems a little bit neater. So there we are. Well done on this question.